will determine the reaction kinetics and also the product selectivity. You can actually observe new reactions. You learn quite a bit about how the molecule is included. It can maybe only be one isomer, which is in there, and in a special configuration. And also intermolecular and intramolecular reactions are employed over intermolecular reaction. Now, this is not a typo. Intermolecular reaction, this means just, it's another term instead of intra. Intermolecular, you mean something is going on within the container, within the cavity. For example, this is one of our working cores, which works quite nicely. You can make this compound very easily, and I'm going to show you later on how we do this. You photolyze this to get an excited state. This can go to diazo compounds. These diazo compounds are much more dangerous to work with. They tend to explode, so you should stay away from those. But these are fairly, we never, in more than 10 years, never had one single accident. So they are very stable, even stable to sulfuric acid up to about 50% of sulfuric acid. If you photolyze them with a bit of nitrogen, you get actually an equilibrium. This would be the transition state. And then you could either get by a 1,2 hydrogen migration, a aromatine, or you could get an insertion where these hydrogens which are here are being inserted and obtain this remember. Now if you look by a 1,2 shift, actually to make aromatine, now that's needs a very high free Gibbs energy of almost more than 50 kilocalories per mole. Also what's going to happen, if we see these orbitals over here, this is not a double bond. This actually is the two p orbitals are not lined up as they should be. One is lined up like this, the other one is going like this, so there is no connection between the two p orbitals. So no double bonds. And actually there were calculations who predicted this. So aromatine has been made by the group of nickel at Boulder, Colorado, but not by doing this way. On the other hand, if you do an insertion like this one here, this needs only an energy of about 12 kilocalorie, and actually you win a lot of energy because the carbines are high in energy, and you go down by about 54 kilocalories per mole. Well, you can do photochemistry, for example, and with cyclodextrines, and the cyclodextrines have lots of hydroxy group. Beta cyclodextrine, for example, has 21 hydroxy groups. So what's going to happen is the carbene inserts into those hydroxy groups, and you get a material, chiral material, which one can actually use as chromatography material for chiral columns. Because so we are working together with somebody here who's in the analytical chemistry division, and you can see you can actually, depending on what kind of complex you use, a 1-2 or a 2-2-1, you can really use specific do insertion into the 6 hydroxy group or into the 2 and 3 hydroxy group. Both reactions actually are possible.
Devam eder. 4. oturumun ilk davetli konuşmacısı Rusya, Moskova'dan Terent'ev, grubu adına sunacağı çalışma New Methods for Peroxide Synthesis.
Dear colleagues, firstly, thank you very much our organizing committee for this invitation conference, and thank you for the possibility to make a presentation about new methods for peroxide synthesis. Firstly, some words about areas of applications of organic peroxides. Traditionally, organic peroxides are used as oxidants in synthesis and as initiators of free radical polymerization. And the more recent trend in peroxide chemistry is medicinal chemistry. For example, for development of drugs with anti-malarial, anti-helminthic, and anti-cancer activity. In industry, a wide range of linear and cyclic peroxides is applied for manufacture of a wide range of high molecular compounds, and from time to time new classes of organic peroxides are introduced in manufacture practice. And recent trend in peroxide chemistry, medical chemistry. About 3 decades ago, it was found that natural compound, artemisinin, is peroxide compound and possess high antimalarial activity. And now artemisinin and its semi-synthetic analogs are widely used in medical practice as the best drugs against malaria and some parasitic diseases. In addition to families of artemisinin, other types of peroxides, mainly cyclic peroxides, possess high anti-parasitic, mainly anti-malarial activity. Because the high cost of natural peroxide and intensive search of synthetic peroxides is carried out, it was found that some ozonides and tetroxanes possess activity similar or more than natural peroxide artemisinin, and these two compounds are on the various stage of clinical trials. And more recent trend of peroxide chemistry is search of compounds with anti-tumor activity. Various types of various classes of cyclic organic peroxides have anti-tumor activity. So the main directions and problems in peroxide chemistry can be formulated as development of selective methods for organic peroxides preparation, selective transformations of organic peroxides, search of biologically active peroxides, and search of effective oxidants and radical initiators. And in the frame of these directions of peroxide chemistry, our work is carried out. We propose general approach for peroxidation of carbonyl compounds. On the first stage, carbonyl compounds are transformed into acetals or enol ethers and followed by hydroperoxidation and with using catalyst produce this hydroperoxide, these hydroperoxidated compounds. The question is, the problem is, in many cases, direct peroxidation of carbonyl compounds is impossible, or as a result of the peroxidation, difficult, practically inseparable mixtures of peroxides are obtained. Using this procedure, using this general methodology, various types of linear and cyclic peroxides were synthesized. On the start of this work, we proposed a method for preparation of geminal bisphenol peroxides by peroxidation of acetals or enol ethers with anhydrous hydrogen peroxide, and it was found that boron trifluoride using as boron trifluoride diethyl as a complex is the best catalyst for the reaction. And using this methodology, various types of geminal bisphenol peroxides were synthesized with good yields. Possibly the mechanism concludes, and possibly on the first stage, boron trifluoride produces a complex with acetal. Then this complex is hydroperoxidated with hydrogen peroxide. Monoperoxidated products is obtained, and again complexation. And in the case of excess amount of hydrogen peroxide, these hydroperoxides are prepared. In the case of limited or absence of hydrogen peroxide, in the reaction mixture, dihydroperoxyperoxides and tetroxanes are obtained as the main products. On the next step, this procedure was used for the synthesis of tetroxanes, mainly unsymmetrical tetroxanes, by the boron trifluoride catalyzed reaction of geminal bishydroperoxides with acetals. This method permits to prepare various types of unsymmetrical tetroxanes with good yields and selectivity. And this methodology was used for the synthesis of peroxides with more large ring, with 9-member ring, namely its traditional name triperoxides. These compounds are applied as intermediates in the synthesis of microcyclic lactones and cyclic alkanones, and as high-temperature initiators for the polymer synthesis. The method for their synthesis is based on the reaction of dihydroperoxyperoxides with acetals or enol ethers in the conditions of acid catalysis. In the course of the development of the method for the synthesis of triperoxides, we found simple and large-scale method for preparation of dihydroperoxyperoxides by condensation 2 molecules of bishydroperoxides under the action of boron trifluoride. Optimization of triperoxide synthesis was carried out on the example of preparation of triperoxide 4 by the reaction of this acetal with dihydroperoxyperoxide 3. For comparison, this compound was obtained using cyclooctanol, ketone, which is starting compounds for this acetal. In the case of using cyclooctanol, only trace amounts, trace yields of target compounds were obtained. But in the case of its acetal, practically quantitative yield of target triperoxide were achieved. By means of this method, various types of cyclic triperoxides can be obtained with yields from good to excellent and with excellent selectivity of the reaction. In addition to boron trifluoride, it was found that iodine, although can be used as a good catalyst for peroxidation reaction. But in the case of using of iodine, the results are different. In some cases, are different from the using of boron trifluoride as catalyst. For example, in the reaction of these acetals with dihydroperoxyperoxides, with using of iodine as a catalyst, only linear peroxides are obtained, no cyclization observed, no cyclization products were found in the reaction mixtures. Using such solvents as tetrahydrofuran and diethyl ethers, various hydroperoxyperoxides can be prepared with good yields. It's interesting to note that in the iodine-mediated peroxidations of enol ethers with bishydroperoxides or dihydroperoxyperoxides, only peroxidation products were formed. In the case of using of small peroxide molecule, hydrogen peroxide, The main products were iodoperoxidated compounds. In the previous part of the presentation, I spoke about mainly about peroxidation of monocarbonyl compounds, monoketones. The peroxidation of dicarbonyl compounds is much more difficult problem because as a result, often practically inseparable mixtures of products of peroxides are obtained. We found very technologically convenient and simple selective synthesis of bridge tetroxides by peroxidation of beta diketones with hydrogen peroxide, and this reaction is catalyzed by acids. The main feature, the main advantage of the reaction, of the simple reaction, concludes in that only in the case of using strong acid, for example, sulfuric acid, at a very high concentration, 2 grams of acid per 5 milliliters of ethanol.
Şimdi burada yaptığımız çalışma NAS territorial anti-inflammatory ürünlerin kontrollü salgını yapacağız. Tabii bu kontrollü salgını nasıl yapacağız? Kontrollü salgını nasıl gerçekleştireceğiz? Bir jel hazırladık. Bu jelin içerisinde de tavsiye ettik. Ve bu jel maddesinin içine ilacın salgını gerçekleştirdik. Jeller hakkında bir kısa bilgi edelim. Jeller sıvıya da tatlı maddelere benzer bir tanesi maddeler. Düşük molekül kütleri olan güreşleri gösterdiği jelleşme de son zamanlarda oldukça ilgi çekti. Mesela nerelerde kullanılır bunlar? Kontrollü ilaç salgılar, sensörlerinde, gıda endüstrisinde, fotoğraf şirketler veya toksik boya giderinde, doku mühendisliğinde potansiyel uygulamaları olan sistemler arasındadır. İlaçların derman ve transdermal verilmesinde derinin oluşturduğu bariyeri aşmada birçok kimyasal ve fiziksel yaklaşımlar kullanılmaktadır. Topikal ve transdermal ilaç verilmesinde yağ diyasterleri ve karşılık yani alkol formlarının enhancer olarak önemi çok büyüktür. Çok sık kullanılan yaklaşım ilaç kombinasyonlarında kimyasal geçişi sağlayan enhancerlar kullanılır. İlaçların derman ve transdermal olarak verilmesinde bazı avantajlar vardır. Bunları böyle istifade ederiz. Biyolojik yardımdır. Kısa olan ilaçların oral yoldan verilmesi, gastrointestinal irritasyonun giderilmesinde, ilacın kontrolü sağlanmalı olana sağlanması, bir de oral yoldan verilmesiyle yan etkilerin önlenmesi, örnek olarak bir ağrı kesicinin tansiyon ilaçlarıyla birlikte kullanılmasını ortaya çıkarken yapacağız. Burada ise çoğu ilacın değişik formülasyonlarında verilmesi, yani değişik formülasyonlardaki formlarını görüyoruz işte. Krem, lozyon, lipozom, miyozom ve jeli görmekteyiz. Biz de burada bu çalışmamızda jel formülasyonunu ağırlıyoruz. Piyasada satılan bazı ağrı kesici ilaçların jel formülasyonları bir şekilde İçinde etken madde yüzdesi, yardımcı maddeler ve ilaçlar etken madde. Düşük molekül kütleri olan o jelatörlerin jel formlarının ilaç taşıyıcı sistem olarak kullanma avantajları vardır. Bunlar nelerdir? İlacın derinden geçişini hızlandırırlar. Yani kanalizasyon özellikleri vardır. Organik karakterlerinden ötürü mikrobiyal kontaminasyona dayanıklıdırlar. Biyo uyumlulukları ve biyo bozulmaları polimerik jelatörlere, yani karbon 941 gibi daha kolaydır. Non-immunojenik özellikleri ilaçların uzun süreli kullanımlarına imkan verir. Orman öjeller nemden etkilenmezler ve orman özel içine ilacın yüklenmesi oldukça kolaydır. Çalışmamızın amacını özetleyeceğiz. İlaç taşıyıcı sistem olarak kullanılan orman özelliklerinden en iyi bilinenleri örneğin lesitindir. Lesitin doğal bir moleküldür. Tabii bu molekülün ihtiyacı karşılayacak olanda temeli olan asıl, yani zor olsa zor. Sentetik biyouyumlu ilaç taşıyıcı orman özelliklerini tasarlamak ve geliştirmek çalışmalarında literatürde oldukça geniş etkilenmektedir. Bu amaçla amino asit bazlı, biz amino asit organik ve çalışmamızın potansiyel taşıyıcı jelatörler olarak kullanılmıştır. Jelleştirme çözücü olarak da yine biyouyumlu, en az özelliği olan yağ asit esterleri kullanılmıştır. kullandığımız organ jelatör yapısı böyledir. Amino ablı kısmı amino asitlerin indirgenmesiyle elde edilen amino ablalardan oluşmaktadır. 6 farklı amid yol yapısı görülmektedir. Tabii güzel denince güzellere ait bazı parametreler vardır. İşte minimum güzel konsantrasyonu, güzelin erimez şartları gibi. Minimum güzel konsantrasyonu açıklayacak olursak, kısacası en az miktarda jelatörün maksimum miktarda çürücü içine alarak oluşturduğu sistemdir. Burada minimum güzel konsantrasyona tayin çalışması görülmektedir. Şurada çürücüler görünüyor. Yağ aslı esterleri. Burada da 6 farklı amid yok. Organ jelatör görülmektedir. Minimum güzel konsantrasyonu en düşük değerlere sahip olan yazı amino ablı kısmının bisfenil alanı, yani kısaca benzer deniz altı olduğu görülmektedir ve transparan jel görülmektedir. Transparan jel görülüyor ve minimum jel konsantrasyonu oldukça düşük. Burada elde ettiğimiz jellerin fotoğrafları görülüyor. Jelin erime noktasını takip ettik. Jelatörün 1 mililitre olan bir çözüdeki 10 mililitrelik iç çaplı demir tüpünde hazırlanan jelinin üzerine 0,250 mg bir yağın bırakılmasıyla bir yağ banyosu sıcaklıkla